today we learned rules of differentiation. You will now be able to take derivatives without having to use limits every time you take the derivative. You're welcome. But do understand that the rules, every one of these rules is proven by using limits. The definition of a derivative doesn't change. All that's happened is they use these rules are proven using the definition. And now you have a rule that you can use every time. And we have several rules we're going to get today. You absolutely need to have these rules memorized and down pat. This chapter, we learn a handful of rules. As we progress, you're going to have to combine them in fun and interesting ways. And you're going to have to use them. And the better you are at what we do in these next two chapters, the better you are at knowing these rules and understanding the rules and applying these rules will make significant difference in the rest of the school year. I cannot emphasize enough. Students that ignore me and don't bother to learn the rules and don't bother to understand and learn how to apply them properly suffer and struggle mightily from here on out. It does make a difference. Every year I've got one or two kids, oh, whatever. And they don't bother, and I have several, and often those are some of the kids that drop at the semester break because they don't spend these next few weeks. There's vital information that you're going to get that you absolutely have to have memorized. Now, some of them really aren't that difficult to get and understand. So, for example, the derivative of a constant. Okay, the derivative of a constant is 0. For example, if f of x equals 5, f prime of x is 0. And this makes sense because if I were to graph 5 as y equals 5, that would be a straight horizontal line. What is the slope of a horizontal line? It's 0. Okay. Oh, I hate this stupid shade. So on the next one here, the power rule. Okay. The derivative of a number raised to a power, a variable raised to a power. Bring the power down out in front, reduce the power by 1. It does not matter what that power is. Positive, negative, fractional, it does not matter. If I have x to some power, bring the power down in front, reduce the power by 1. So, if f of x is equal to x cubed, f prime of x is 3x squared. Bring the power down in front, reduce the power by 1. Okay? Once again, it does not matter what the exponent is. It works for any exponent, positive, negative. Your book actually has 2 rules, one for negative exponents, one for positive exponents, but it's the same rule. I don't know why they have 2 rules. Okay? If it's a fractional exponent, this is how you take the derivative of a square root. The derivative of the square root of x. Rewrite the square root of x as x to the 1/2 power, and then apply this rule. Okay? You cannot do it as a square root. You must make it a fractional exponent. Once you make a fractional exponent, this rule applies. Okay. Okay, you will notice the notation. Okay, you will notice the notation is a little goofy. So the constant multiple rule. If u is a differentiable function of x, u is not a variable. U is not a constant. U is a function. Okay, u is a function in this case. So the derivative of a constant times a function, and u is a function of x. So the derivative of a constant times a function of x is the constant times the derivative of x. the derivative of a constant times a function of x is the constant times the derivative. Okay, so for example, f of x is 5x squared, 5x cubed. The derivative, I should actually do it this way, the derivative with respect to x of 5x cubed is 5 times the derivative of x cubed. Okay, it's the derivative of x cubed, which, so the derivative is 5 times 3x squared, which is 15x squared. Okay, so obviously it's not that big. It's generally speaking not that big of a deal. You still bring the power down in front, but what do? You multiply the power times the constant out in front. Where this becomes more important, with polynomials, it's not a big deal. But where this becomes more important is when we have other functions going on. If I have 3 times the secant of x, okay, the derivative of the secant of x, which we will get next week, is a complicated function. It's a complicated rules. Pull the 3 out first, take the derivative of the secant, then tag the 3 back on when you're done. It's a lot easier that way. It's often easier. Pull the constant out, do the derivative, and then put the constant back on the front. It's just sometimes that's what they are. Okay? Questions? Okay. Sum and difference rule. If u and v are differentiable functions of x, then the sum and difference are and their sum and difference are differentiable at every point u and v are differentiable. What this basically says, if I have individual things that are added and subtracted, I can take the derivative of the first thing plus or minus the derivative of the second thing, plus or minus the derivative of the third thing, plus or minus the derivative of the fourth thing. If I have things that are added and subtracted, it's the derivative of each individual item. I don't have to do as in full, I can do it part by part by part by part. If it's addition, subtraction. Muy importante. This only works for addition, subtraction. So, for example, if f of x is 2x to the fourth minus 5x cubed plus x squared minus 4x plus 1, I just have to take the derivative of each term individually. F prime of x, the derivative of 2x to the fourth. Bring the 4 down out in front, reduce the power by 1. 4 times 2 gives me 8x cubed. Minus the derivative of 5x cubed, which you actually already did up there, so it's minus 15x squared. The derivative of x squared would be, what? 2x. Bring the power down in front, reduce it by 1, 2x. Here's the hard one. What's the derivative of negative 4x? Negative 4. What's the power on negative 4x? The power is 1. Bring the 1 down out in front, reduce it by 1, so that gives me negative 4x to the 0. X to the 0 is 1, so it's negative 4. And the derivative of 1 is 0. Sorry, it's down at the bottom. I can't get this to extend and move up because I got the stupid shade thing on it. Okay. Questions? Not difficult, is it? But these are all polynomials and versions of polynomials. Polynomials are the easy ones. He says with a wicked grin. Okay, the product rule.
Wait,
Yeah, I can go back. Yeah. How's that? There, that's like Karina.
Beautiful.
Like I said, polynomials, you'll like polynomials. You'll come to really appreciate the ease of polynomials as we progress through the year.
Why are they so easy?
Because they're the simplest functions you work with. Realistically speaking, they are the simplest. Well, trig functions get complicated. Logarithms, exponentials, they get complicated. Boy, wait till we have a variable in both the exponent and the base. You're going to hate that one. But you got to know. Are we good? Okay. Product rule. The product of two differentiable functions, u and v, is differentiable, and the derivative of a function u times a function v is u times the derivative of v plus the derivative of u times v. The derivative of the first times the second plus the derivative of the second times the first. If you have three objects multiplied, you take the derivative of each one in turn, leaving the other ones alone. And you add them together. You do not take the derivative of the first times the derivative of the second. The product rule is not the sum and difference rule. It is much more complicated than that. And you absolutely, this is one where I can tell when students are lazy, not paying attention, and not studying. This is the first place I can see it. Because when you take the derivative of a product and they do the derivative of the first term times the derivative of the second term, then I know they weren't paying attention and they didn't learn the product rule because it's different than the sum and difference rule. It is not the same. I know with limits, the limit of the first, limit of two things, the limit of the first times it does not work with derivatives. It's not the derivative of the first times the second. It's the derivative of the first times the second plus the derivative of the first, the derivative of the second times the first. If I have two things that are multiplied that I'm taking the derivative of, I'm going to have two objects added together. Okay. So, for example, okay, f prime of x equals, if this is my first object, the derivative of x squared plus 1 would be, what? 2x. Times the second term, unchanged, plus my first term, unchanged, times the derivative of my second term. What is the derivative of x cubed plus 3? 3x squared. Derivative of the first times the second. Derivative of the second times the first. If there are three things, then you do that 3 times, progressing your way through the 3 things. Okay. And now we simplify. 2x, so we get 2x to the 4th plus 6x plus 6x to the 4th plus 3x squared. So f prime of x equals 8x to the 4th, right? Yeah. Plus 3x squared plus. Oh, that should be 3x to the 4th. My bad. My bad. So yeah, that should be 3x to the 4th. So this would be 5x to the 4th. Thank you. Now, so that is a poorly worded question. I'm just now realizing how poorly worded it is. But the question is, could I have FOILed this out first and then taken the derivative? Yes, I could have. Would I get the same answer? Yes, I would get the same answer in the end. Okay. Sometimes it's easier to do that. Sometimes it's not. Depends upon how complicated the things are that you're putting together. If I start adding exponents, if this was x squared plus 1 to the 5th power and x cubed plus 3 to the 6th power, oh, you do not want to FOIL that out, make one term, and then go from there. You want to use the product rule and then simplify from that point on. We will learn how to do that coming up in the next chapter. Okay. So yeah, you can sometimes simplify it first, then take the derivative. Sometimes you want to do that. Sometimes you don't. Depends on how complicated it is. One of your homework assignments is doing this with the product rule and doing it without the product rule by multiplying it out first, so that way you can see that they are the same thing. And if you thought the product rule was fun, you're going to love the quotient rule. It's very similar to the product rule, with a couple of major exceptions. One, you're not adding the two terms. You still take the derivative of the first times the second, derivative of the second times the first, but you are subtracting them. So order is important. Divided by the denominator squared. So it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. That'll make it easier to work. Okay. Now, if we pause for a second, often, this is using straight out of what the textbook uses. What I often use as well, and what I will often refer to is the derivative of f over g. This is u and u instead of u and v. Same thing. The derivative of f divided by g. F prime g minus g prime f all over g squared. I will often do that. I use what the textbook uses on this. U and v's are very common in what they do. Okay. Yeah, it's the derivative of the first term. First derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. So, to work the example. So if I want to take the derivative of this, f prime, the derivative of my numerator, and that's x squared plus 5x minus 1. And I don't know why it got compressed. And I've tried to uncompress it. It won't uncompress for me. I'm not sure why it did that. And it won't uncompress for me. It really pisses me off. X squared plus 5x minus 1. So my derivative is 2x plus 5 times my denominator, x squared, minus the derivative of my denominator, 2x, times my numerator, x squared plus 5x minus 1, all over x squared squared. Notice, I did not do any simplification. All I did was take the derivatives, write things down. I know what my denominator is. My denominator is x to the 4th. I know that's what it is. However, I'm not going to mess with it right now. Okay? That doesn't mean that we're not going to leave it alone. Okay, distribute. So I get 2x cubed plus 5x squared, and then distribute a minus 2x. So I get minus 2x cubed, and then minus 10x squared plus 2x all over x to the fourth. And my 2x cubes actually cancel each other out. Sometimes it happens, sometimes it doesn't. Don't count on it. 5x squared minus 10x squared negative 5x squared plus 2x all over x to the fourth. Can that be simplified more? Yeah, I can take an x out of every term. Once again, your algebra skills will be really good when you're done with this class. Really good algebra skills when you're done with this class. Now, so is there another way to take the derivative of this function? Yes, there is. What you could do is break it up into several individual fractions, but that's only because my numerator, the only reason I would contemplate doing that is because my original denominator was a single term. Because I have a single term down here, I could make it into several individual terms. X squared over x plus 5x over x squared plus minus 1 over x squared, and do those. But if I have something more complicated than basically a single term down here, I don't break it up. If I've got anything more than a single term in my denominator, I don't do that. I do the product rule. And you need to practice product rule with stuff that's relatively easy. Yes?
All right, so go over the first part, the derivative.
This here?
Yeah.
Derivative of the numerator.
That's the
Denominator.
That's the,
Minus the derivative of the denominator.
and that's just the
Numerator over the denominator squared. And like I said, you got to learn the rules. You got to have them memorized. Okay. So, higher order derivatives. Not just derivatives, but higher order derivatives. Those are just derivatives of derivatives. Of derivatives. Of derivatives of derivatives of derivatives. Okay. So you have y prime, y double prime, y triple prime. Now, with the derivatives, and you'll see more often the derivatives where you want second or third derivative written as the notation written as it's shown below that. dy dx is the first derivative. d2y dx squared. d3y dx cubed. Technically, I should rewrite them, or I can rewrite them as second derivative of y with respect to x. That's what that means. It's the second derivative of y with respect to x. The third derivative of y with respect to x. That's what higher order derivatives are. You just take more than one derivative. So for example, suppose y equals x squared plus x plus 1, find y double prime. Okay, first I have to find y prime, the first derivative. The derivative of 2x, x squared is 2x. The derivative of x is 1. Y double prime is the derivative of y prime. Take the second derivative, you just take the derivative of the first derivative. You want the third derivative, you take the derivative of that, and so on and so forth. It would just be 2. What is the third derivative? 0. What's the fourth derivative? What's the fifth derivative? What is the 100th derivative? 0. With polynomials, eventually they will disappear. They will disappear with one more derivative than the highest power. Eventually, it will become 0. With one more derivative than the highest power. That happens with polynomials. Other functions, it gets more complicated. Gentlemen, questions?
Yeah.
Okay, what?
So y double prime, that's the derivative of the derivative.
Yeah, second derivative.
So what is that?
It's okay. We do what I. Okay. So no. That's a very good question. Okay. So if I have a function that describes where something is,
Okay.
where an object is, we will actually be using what's called rectilinear motion. We have a point moving back and forth along the x-axis. Its location is described as x of t. Its point at a particular time t is where is it on the x-axis. That's its position. The derivative of that is its velocity. It's moving back and forth. The derivative of the velocity is the acceleration. So if you have a function that describes where something is, the second derivative describes its acceleration. Now, what's really cool is there is an application for the third derivative. It's called jerk. No, really, it is. It's called jerk. I saw a T-shirt that says "Don't be a," and they had the third derivative on there. Don't be a jerk. Okay, there are not many people going to get that one. Okay, but yeah, there are applications, and we will be using a lot of second derivatives. Chapter 5 is applications. First 3 sections are all about taking equations to graphs and analyzing equations graphically using derivatives. There's a full section that is nothing but the second derivative and how it relates to graphs of functions. It will become an important thing. But if you're talking practical application, motion is the easiest one to describe. The derivative of the derivative gives you acceleration. But you may also think about it as how fast is that rate of change changing. Okay, so I'm making money at a particular rate. So I have an equation that describes how much money I have. The derivative of that tells me how fast I'm making the money or how fast I'm losing it.
And then what's the derivative?
The derivative of that would tell me, is my rate of change increasing or decreasing? Am I going to start making money even faster, or am I going to start making money even slower? How is that going to change? I can use that for prediction. So it is actually very useful. It is very useful.
Wait, so is it basically just the slope of the slope?
It is, but there's a little more to it than that. Okay. One last thing. Okay, this is muy importante for understanding several of your homework questions, and we will have similar homework questions as we progress through the year. AP questions are starting to look like this from time to time now. I've seen some that look like this. U and V are not variables. U and V are functions. U and V are just like F and G and H and all that kind of stuff. They are functions. They're not actual variables. They're functions. Now, I'm given y is equal to u times v. What is y prime of 2? Is my question. So to answer this, I go, well, first of all, what's y prime? U and v are functions, so what do I use? The product rule. U prime times v plus u v prime. Or v prime u, either way, doesn't matter. So that's the derivative of y is using the product rule. U and v are functions. We don't know what they are, but they're functions of x. So y prime of 2 would be u prime of 2 times v of 2 plus u of 2 times v prime of 2. And from there, just plug in the numbers. That's why they give you those values. It's often done like this or done as a table of values. You will see an awful lot where here's f at certain places, here is f prime at certain places, here is g at certain places, here's the value of g prime at certain places. Like I said, from here you just plug in the numbers. Y prime of 2, u prime of 2 is -4, v of 2 is 1, plus u of 2 is 3, v prime of 2 is 2, -4 plus 6 is 2. So y prime of 2 is 2. Okay?